For decades, commercial aircraft have relied on well-established systems for thermal control. Large structures, controlled environments, and active cooling methods that keep electronics safe at any altitude. Urban air mobility introduces a different set of constraints: smaller vehicles, tighter enclosures, and higher power densities. There's limited room for airflow, limited access for cooling hardware, and virtually no tolerance for failure. As systems become more integrated and compact, thermal management becomes one of the most critical design challenges. Here, at the University of Arizona, our senior design team set out to design and validate a passive cooling system for avionics hardware, a system that could operate under extreme thermal conditions, across a wide range of environments, and meet strict spatial constraints, all without moving a single part. This is how we did it.
Hi, I'm Stevie Robbins. I'm studying aerospace engineering, and I'm the CAD and machining lead.
Hi, I'm Miguel Barrera. I'm studying aerospace and mechanical engineering, and I'm the structural and procurement lead.
Hi, I'm Cody McManus. I'm studying mechanical engineering, and I'm the thermal lead.
Hi, I'm Al Balik, studying electrical engineering, and I'm the electrical lead.
Hi, I'm Raul Magano. I'm studying aerospace engineering, and I'm the integration and validation lead.
And I'm Sarah Lee. I'm studying systems engineering and the team lead for team 25028, avionics size reduction and thermal reliability enhancement.
Our project is referred to as the Thermal Reliability Enhancement System, or TRACE for short. It's a low size, weight, and power, or SWAP, thermal management system designed for a miniaturized avionics platform with a focus on passive cooling strategies. We had to meet strict design requirements, including fitting everything into a compact size envelope of 6.7 by 1.8 by 3.95 inches. That's with mounting tabs and connector protrusions included. The system could not exceed 850 grams, and it needed to be fully sealed, with no visible openings or moving parts. Our design uses copper heat pipes with water as the working fluid, along with a custom aluminum fin assembly and thermal interface materials. We also built a custom enclosure and central support frame, and included polyimide heaters to simulate internal heat loads based on real avionics operating conditions. Since the actual avionics boards are proprietary, we had to use these polyimide heaters instead. These were mounted on aluminum cutouts that mimic the size and thermal behavior of the real circuit boards for testing and validation.
TRES leverages heat pipes, capillary action, and phase change principles to transport and dissipate thermal energy without any mechanically moving parts. While traditional cooling solutions depend on forced convection, our design optimizes natural convection and conduction. With water as the working fluid inside the pipes, heat transfers via conduction through the avionics boards and central frame, at which point the pipes are then heated up. As the heat pipes increase in temperature, the water in the pipes near the heat sources undergoes phase change from liquid to a superheated vapor. At this point, we observe capillary action in motion as the superheated vapor begins to travel along the central channel of the pipes towards the cooling zone, which is the fin assembly. There, the heat is then drawn through conduction into the fins, which are simultaneously cooled through natural convection within the outside air, resulting in the heat being drawn away from the pipes. This results in the vapor inside the pipes being cooled and condensed back to a liquid before traveling along the wick structure, which is composed of either a porous media or group channels towards the heat source to repeat the cycle. This process enables effective cooling without any external energy input. Our central frame acts as both structural support for the enclosure and avionics boards, as well as a direct conductive path between the heat-generating components and the heat sinks. Additionally, unlike most designs that prioritize ventilation, our fully sealed enclosure demonstrates that effective heat dissipation can be achieved without direct contact between the avionics boards and external airflow.
As mentioned earlier, there were several different requirements TRACE needed to meet. Here you can see the requirements span across performance, environment, safety, and design features. In total, there are 12 different requirements, and of those 12 requirements, the major ones that drove the design are highlighted here. This includes thermal dissipation capabilities, operation in ambient, cold, and hot environments, size, weight, production cost, and no visible openings on the enclosure. To evaluate the thermal performance of our design, we conducted simulations in SolidWorks flow simulation under ambient temperatures of 5, 22, 50, and 70 degrees Celsius, with a low external airflow of 0.05 meters per second to mirror thermal chamber conditions. Despite this, the system remained operational, only reaching 102 degrees Celsius at 70 degrees Celsius ambient. In typical conditions, with 0.5 meter per second airflow, this would stay well below our 95 degrees threshold.
Parallel to simulations, physical testing was performed in a thermal chamber. Thermal chamber tests use thermocouples and FLIR imaging to measure internal air and surface temperatures. At 5 degrees Celsius, internal air temperatures between circuit card assembly 1 and circuit card assembly 2 were 28.5 and 23 degrees Celsius. At 22 degrees Celsius, the internal temperatures rose to 54 and 47.5 degrees Celsius. At 50 degrees Celsius, these values became 72.5 and 65.5 degrees Celsius. Finally, at 70 degrees Celsius, max temperatures were recorded as 92.5 and 87 degrees Celsius respectively. However, in all cases, we remained under the 95 degrees Celsius internal air temperature limit. Surface temperatures remained safe at lower ambient conditions and peaked at 73.9 degrees Celsius during the 70 Celsius test. Anticipating this result, our enclosure features a safety label indicating these unsafe touch temperatures.
Simulated temperatures closely aligned with physical data, especially at 22 degrees Celsius. Deviations in surface readings were linked to aluminum reflectivity and airflow modeling assumptions. Between our simulations and thermal chamber test values, our circuit card assembly 1 errors range from 0.97% to 24.3%. Our circuit card assembly 2 errors range from 12.9% to 38.9%, and our surface temperature errors range from 26.8% to 57.3%. Confident in our simulation results, we compared our simulations without trace to physical tests with trace, and we saw card temperatures drop by 22.7 degrees Celsius at 22 degrees Celsius ambient and over 31 degrees Celsius at an external temp of 70 degrees Celsius, representing 31% and 26% temperature reductions at these two environmental temperatures. On top of staying within all of our design feature requirements, such as size, mass, and cost constraints, our project met all thermal and functional goals, demonstrating reliable avionics operation across varied environments.
One of the biggest takeaways from this project was the importance of collaborative problem solving and supporting each other as a team. We had a lot of late nights, shared plenty of laughs, and learned a lot along the way. Thank you to our class mentor, Doug May, our project advisor, Jay Crossman, and our company sponsor, Akron Aviation, for all the support and for giving us a chance to work on this project.